welcome to the deep dive. If you are building software right now, you definitely know the story. You watch a demo of a new AI coding agent, and it looks, like pure magic.
Oh, yeah, it just effortlessly spins up this complex React component.
Right. It wires up the back end perfectly, and you're just sitting there thinking, wow, this changes everything. But then, you actually deploy it into your own production environment.
Right, the messy reality of a real code base.
Exactly. You handed a real workflow with like 30 conversation turns, 15 different tool definitions, this massive mountain of retrieved documentation, and the magic just completely vanishes.
It falls apart so fast.
It really does. Suddenly, this brilliant AI is like hallucinating variables, totally ignoring your direct instructions, picking the wrong tools, and falling into these maddening, endless loops.
And the immediate reaction, which is totally natural, is to just blame the model. You watch it fail to fix like a simple bug in a Python script, and you assume the underlying LLM just isn't smart enough yet for enterprise-grade work.
Yeah, you think, oh, GPT-4 or Claude or whatever, it just isn't there yet.
Exactly. But we are actually looking at the wrong culprit here. The model didn't suddenly get dumber between that polished demo and your production environment.
Okay, let's unpack this. Our mission for today's deep dive is to dig into a whole stack of recent technical research papers and engineering guides to figure out why this breakdown actually happens to your agents.
And, more importantly, how to solve it.
Yes, exactly. We are going to build a concrete, actionable workflow to fix it in your own stack. Because we aren't looking at how to prompt an AI today, we're looking at how to architect its memory.
Yeah, what we are really dealing with here is a failure to distinguish the symptoms of AI failure from the actual root cause. So our goal today is to isolate that root cause and then construct a real engineering-grade solution.
To put it in perspective for you, think about current coding agents, like a brilliant senior developer, just a 10x engineer. But imagine forcing that developer to work while someone is standing right next to their desk, constantly dumping thousands of pages of raw server logs, outdated manuals, and completely irrelevant code snippets right on top of their keyboard.
That's such a good visual because they aren't failing due to a lack of coding skills.
Right.
They are failing because they are just suffocating under the sheer volume of noise.
Yeah. So before we can engineer a solution, we must correctly diagnose what is actually breaking. Those symptoms you just mentioned, the hallucinations, the ignored instructions, the endless loops where the agent tries to fix a bug, fails, and then just rereads the exact same massive file again.
Yes, the dreaded read, try, fail, reread loop.
It's the worst. You just sit there watching your terminal window as the agent just, burns through API credits, spinning its wheels on the same 5,000-line file over and over.
Yeah.
But hang on, I want to push back here for a second.
Sure, go for it.
Because I'm paying premium API costs specifically for a 128K or even like a 200,000 token context window, so I don't have to worry about this.
Mm-hmm.
Are you telling me that massive window is just a marketing gimmick if I don't format my code right? Like, shouldn't simply giving them massive context windows natively solve this problem?
It's a really fair assumption to make when you look at all the marketing materials out there, but it highlights a really fundamental misunderstanding of how these models allocate attention.
Okay, how so?
Well, the root cause of the breakdown isn't a lack of space. It is a failure in context engineering. You have to remember, the context window is prime real estate. And just because you have 200,000 tokens doesn't mean the model can reason effectively across all of them simultaneously.
Ah, right. It's not a hard drive.
Exactly. There is this well-documented phenomenon in the research known as being lost in the middle.
The U-shaped performance curves.
Yeah, got it. If you plot a model's ability to recall and actually utilize information against where that information is located in the prompt, it forms this severe U-shape.
So it only remembers the ends.
Right. The model reliably remembers what you put at the very beginning, like your system instructions, and what you put at the very end, like the user's immediate question. But anything buried in the vast middle of that massive context window?
It just disappears.
Pretty much. The model's attention dilutes, and it effectively becomes blind to it.
Which is terrifying when you realize what actually goes into a production agent's context window.
Yeah.
If you're building an agent right now, you've probably seen this. By the time a user actually types a single word, 60% to 80% of your agent's context window might already be consumed.
Oh, easily.
You've got, 1,500 tokens of system prompts, maybe 5,000 tokens defining 20 different tools, plus the entire conversation history. The agent is practically exhausted before it even starts the task.
And the research highlights a truly shocking statistic on this exact front. Coding agents often spend a massive chunk of their entire token budget simply on read operations.
Wait, how massive are we talking?
76.1%.
Over 75% just read.
Just reading. That means executing raw file dumps, running broad code-based searches, and, pulling in massive amounts of surrounding text just to find a single relevant function.
Wow.
The cognitive budget is being totally squandered on noise, leaving almost no attention span for the actual reasoning required to write the code.
So treating the context window like this limitless landfill clearly doesn't work. We can't just keep buying bigger desks for that developer. So how should we conceptualize an agent's memory?
Well, if we connect this to the bigger picture, we don't actually need to invent a new paradigm here. We can borrow a foundational concept directly from traditional computer science.
Okay, I'm listening.
Operating system virtual memory paging.
Oh, that makes perfect sense for our audience. So in standard computing architecture, you have your disk, which is massive storage, but high latency. And you have your RAM, your main memory, which is extremely fast, but highly limited.
Exactly. And you never load your entire hard drive into RAM just to run a single application.
All right, the operating system pages specific chunks of information in and out of RAM, exactly where the CPU needs them, and then it evicts them when it doesn't.
Yes, and we need to treat the LLM's context window as the agent's RAM. External data, so your code base, the vector databases, the API documentation, that is the disk. The agent must page information in and out.
Just moving chunks back and forth.
Right. And to do this successfully, developers really have to distinctly separate 3 different operations that constantly get conflated.
We'll try.
Retrieval augmented generation, or RAG memory, and context engineering.
Right, because they are completely different layers of the stack. Like RAG is your search engine, right? It retrieves candidates from the disk. Memory is your persistence layer. It saves state and facts across sessions, so the agent doesn't have amnesia. But context engineering, that is the active gatekeeper.
The active gatekeeper. That is a really great way to frame it, because just because RAG found a file or a fact is persisted in memory, that does not automatically grant it access to the context window. Context engineering is the deliberate programmatic selection of what actually earns a spot in the prompt for this specific turn of the conversation.
I really want to highlight that for you because it is the crucial pivot point. Retrieval and context injection must be separate decisions in your code. Just because your search function found a 10,000-line configuration file does not mean the LLM needs to read every single line of it right now.
Exactly. Finding the file is step 1. Deciding what parts of it get loaded into RAM is step 2.
So let's translate this OS framework into a concrete workflow for your engineering stack. Step 1 of this workflow is all about measuring the waste and optimizing the cache. We start with context budgeting.
Right, because you can't fix what you aren't logging.
Exactly. So what does context budgeting look like in practice?
Engineers must implement a context budget calculator directly in their middleware. Basically, before any LLM call is fired off, you programmatically calculate how many tokens are being consumed by the system prompt, the tools, the history, and the retrieve docs.
And is there a specific threshold they should look out for?
Yes. The golden rule of thumb found in the engineering guides is this. If your utilization is over 60% before the user even provides their input, it requires immediate intervention in your code.
Because at that point, you're leaving the model no room to reason.
Right. You are virtually guaranteeing it will get lost in the middle.
Okay, so once we have that budget under control and monitored, we have to talk about the cache, specifically prompt caching. If you are building right now, this is a relatively new feature offered by major LLM providers, and it is just a total game changer.
Absolutely.
It can reduce your API cost by up to 80% and drop your time to first token latency by up to 31%. I mean, it's basically free money and speed if you architect your calls correctly.
And what's fascinating here is the underlying mechanics of how that cache actually functions on the provider's servers and why so many developers accidentally break it without even realizing it.
All this happens all the time.
Because prompt caching requires exact prefix matches. The provider computes the KV cache, so the attention states for a sequence of tokens. If your next API request starts with that exact same sequence, it reuses the computation. It skips all that heavy lifting.
Right, it just grabs it from memory.
But if even a single token changes at the beginning of your prompt, the cache breaks entirely, and the server has to recompute everything from scratch.
And this is where the operational mistake happens. I've seen so many developers inject dynamic data into their system prompts. They'll put like the current timestamp, unique session ID, or the dynamic output of a database query right at the top of the context.
Thinking it's helpful context for the agent.
Exactly. But by doing that, they're silently destroying their cache hit rate. Every single turn of the conversation looks like a brand new prompt to the server. You are paying full price every single time.
So the actionable fix requires real structural discipline in your API calls. You must keep your system prompt, the core instructions, the persona, the static rules, entirely static.
And don't touch it.
It should be identical across every single request. You take all that dynamic data, the conversation history, the shifting tool results, the retrieved file chunks, and you append them to the very end of the prompt structure.
That makes total sense.
Yeah, this maximizes the cacheable prefix, ensuring that the heavy computation of processing your core instructions is only paid for once.
Okay, so we've restructured our API calls, our cache is stable, and our budget is being monitored. We've optimized the RAM at the system level. But even with a perfect cache, if you dump a massive monolithic codebase file into the prompt, you'll still blow past that 60% budget limit instantly.
Oh, for sure.
So how do we shrink the codebase before the agent actually sees it?
This brings us to the second part of our actionable workflow, which is intelligent pruning. You see, when an agent needs to look at code, the default kind of lazy approach is usually to just give it raw command line tools.
Yeah, you give the agent a grep tool, or cat, and tell it to go find the bug. But giving an AI raw grep is treating code as if it's just a flat, dumb sequence of characters. It searches for a keyword like, author, and pulls in massive unformatted chunks of text. It pulls in hundreds of lines of irrelevant comments, boilerplate, disconnected logic.
Because code is not flat text. It is highly structured hierarchical logic. Modern agents must use abstract syntax trees, or ASTs, to parse and understand the code base.
Right, ASTs.
Using libraries like TreeSitter, an AST parses the code into this beautiful hierarchical tree structure. It actually understands what a class is, what a method is, and how variables scope to each other. It provides deep semantic understanding, not just blind keyword matching.
Okay, but if a file is too long, say it's 3,000 lines, can't we just use standard prompt compression to strip out tokens and save space? Like, those open source tools that just drop out vowels or low information words to aggressively compress the prompt before sending it?
I am so glad you brought that up, because the research issues a very strong warning against doing that. You absolutely cannot use token level pruning for code.
Wait, really? Why not?
Well, in natural language, if you drop a few words, the LLM can still infer the meaning. But code is incredibly brittle. Token-level pruning disrupts code syntax and completely destroys AST correctness.
Oh, because it breaks the compiling logic.
Yes. In rigorous tests, applying standard text compression to code dropped its syntactic validity to near 0%.
Wow, 0%. So you basically end up feeding the agent broken, uncompilable gibberish, which perfectly explains the hallucination symptoms we talked about at the very beginning. The agent is trying to fix a bug based on code that is fundamentally broken in its own context window.
Exactly.
So if we can't compress the tokens like that, what's the actual implementation for pruning?
Engineers must build line-level task-aware pruning pipelines. It's a multi-step process. First, when the agent decides it needs to retrieve a large file, the system actually intercepts that request. The agent is forced to generate what's called a goal hint.
A goal hint. So it has to explicitly declare its intention before it gets the file.
Right. It explicitly states what it's looking for. For example, the agent outputs something like, focus on error handling for the database connection. Then, your backend takes that massive raw file and the goal hint and passes both of them to a lightweight neural skimmer.
Let's make that concrete for the listener. What exactly is a neural skimmer? Are we talking about training a custom model here?
Oh, not necessarily. In practice, you just use a much smaller, faster, and cheaper model, something like GPT-4 Mini or Claude Haiku.
Okay.
Its only job is to evaluate the massive file line by line against the agent's goal hint. It retains only the semantically relevant lines while simultaneously using the AST to ensure the surrounding logical structure, like your class definitions, imports, bracket, closures, remains perfectly intact.
That is just brilliant architecture. You're using a lightning-fast, cheap model to read the whole file so your expensive, slow reasoning agent doesn't have to. And the results of this are wild.
The token savings are huge.
Yeah, the research shows you can achieve up to a 14x token reduction using this AST-aware pruning. You're turning a noisy 3,000-line repository dump into a compact, pristine evidence packet. It contains exactly the logic the agent needs to see and nothing It doesn't.
And it fundamentally shifts the primary agent's workload from parsing noise to actual reasoning.
Hmm.
But, optimizing the retrieved code is really only half the battle of context engineering. We also have to optimize the tools we are giving the agent to work with.
Right, so we've shrunk the code files down, but what about the instructions we give the agent to process that code? Let's look at the skills and tools we arm our agents with, because the stats here highlight a massive operational blind spot.
Yeah, this part is pretty eye-opening.
There was a comprehensive study that analyzed over 55,000 public agent skills, and they found that 26% of them lack routing descriptions entirely, meaning the agent has to read the entire body of the tool just to figure out what it's even supposed to do.
Which is just awful for the context budget.
Right? And worse, over 60% of the body content within these skills is completely non-actionable background text, verbose explanations, or redundant templates.
It is the literal definition of bloat. And remember our context budget. Every single token of that non-actionable content is injected into the context window, eating up your 60% budget limit and further diluting the model's attention away from the actual task.
It's like hiring a master carpenter to build you a custom cabinet, but forcing them to carry the entire hardware store on their back just to hammer a single nail. It's exhausting, it's totally inefficient, and it's no wonder the carpenter eventually makes a mistake.
That analogy is spot on. And the solution to this is applying the principle of separation of concerns through what we call progressive disclosure. We have to stop loading monolithic tool definitions into the context window.
Progressive disclosure, meaning revealing information only as it is strictly needed. So how does a developer actually build that for an AI agent?
It requires restructuring how your backend serves tools to the LLM. By default, the agent should only ever load the core actionable rules, just the absolute minimum JSON schema required to understand that a tool exists, what its inputs are, and what it returns.
Just the hammer, not the whole store.
Exactly, just the hammer.
Uh-huh.
All of the supplementary material, the complex edge case examples, the massive JSON templates, the dense background documentation that all gets deferred, you place it into on-demand modules.
Oh, I see.
The agent can request those specific modules via a separate tool call, but only if it actually hits an edge case and needs them for the immediate task.
Which ties perfectly into dynamic tool injection. Instead of dumping all 20 of your available tool definitions into the prompt at the start of a session, which, as we know, ruins your prefix cache and bloats your budget, you use a lightweight classifier.
Yes, this is where that smaller model comes in again.
Right. Before the main agent even takes a step, you make a 50 millisecond call to a cheat model. It looks at the user's request and outputs a simple JSON array predicting which 3 or 4 tools are actually relevant right now out of your entire toolbox.
You prune the toolbox.
Exactly. You only inject those specific tools into the context window. You save thousands of tokens, you protect your cache, and most importantly, you focus the main model's attention. Give it fewer options, and it makes better, faster decisions.
This raises a really important question about the architecture we are building here, because whether it's caching the prefix, skimming the code into an evidence packet, or dynamically injecting only the necessary tools, every single technique is about ruthlessly protecting that virtual memory.
Right. So let's summarize this workflow so you can take it straight to your code base. We started by diagnosing the real pain agents failing in production isn't because the underlying LM are dumb, it's because they are hitting a context wall.
Right, the root cause is a failure in context engineering.
Exactly. And to fix it, you need an operating system memory model. First, calculate your token budget and set hard alarms in your middleware if you hit 60% utilization before user input. Second, protect your prefix cache to save money and latency. Keep your system prompts strictly static and push all dynamic data to the very end of the API call.
That one is so crucial.
Oh yeah. Third, stop giving agents raw text tools like grep. Use ASTs and line-level pruning with goal hints, utilizing smaller models to compress massive files into tight evidence packets. And fourth, cure skill bloat using progressive disclosure. Dynamically inject only the core tools needed for the immediate step and keep the heavy documentation filed away until requested.
And as we implement these OS-level memory structures, the AI agent is no longer just a passive reader trying to absorb a massive, disorganized document.
Yep.
It is actively curating its own reality. By defining its goal hints and pulling in only specific evidence and tools, it governs its own context.
So what does this all mean?
Well, it leaves us with a provocative thought to consider. Does this mean the future role of the software engineer will shift fundamentally?
In what way?
Perhaps we are moving away from writing raw logic, and instead our primary job will become architecting and governing the attention span of our AI systems.
Governing the attention span. I really love that. You aren't managing the code directly. You are managing the carpenter's environment so they don't have to carry the whole hardware store on their back. Well, thank you for joining us for this deep dive. Take this workflow, apply these memory constraints to your next agent build, and just watch how much smarter your model suddenly becomes when you clear off its desk.